Along in this lecture, we'll find out the area of a circle using two different methods. In the drawing, we have a circle, and we have also this is square ABCD. This is line 7AP, is equals to 1 inch length. This is line 7QC, that is equals to 4 inch length. Again, our mission is to find out the area of this circle. So we'll start with the first method. All the angles inside square ABCD are right angles. So those two angles are all right angles. So this is a right angle. This is a right angle. This is also a right angle, and this is a right angle. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent AB with this circle. This point is point S. And we will join points O and S together by a straight line. Line segment OS is the radius of this circle. We define the radius of this circle as x. So S equals to x. Here we can implement rule 1. So we fit to rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle, and this is tangent AB, that is tangent to this circle, it's point N. In addition, we have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. So can we actually implement rule 1 in our drawing? Why? Because in our drawing, we have the radius OS that is equal to x. The radius OS is drawn. The radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will join points O and Q together by a straight line. Point Q is the point of tendency of tangent BC with this circle. Line segment OQ is of course the radius of this circle that is equal to x according to our definition. The radius OQ is equal to x. The radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QC. If BC is perpendicular to QC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral SBQO, we have 1, 2, 3 right angles. The sum of three right angles is 270 degrees. 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral SOQB we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be at least a rectangle if not a square. So remember, to quadrilateral SOQB is a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SUQB, side SO must be equal to the opposite side QB. But SO is x, therefore QB must be also equal to x. Likewise, according to the sum rule, in the sum rectangle SOQB, side OQ must be equal to the opposite side SB. But OQ is x, therefore SB must be also equal to x. So if we found out that quadrilateral SOQB is not a rectangle but a square, well, because of the fact that all of its sides are equal to each other. Each side of the square equals to x units in its length. We know that all the sides of any square are equal to each other. That is to say, side AB equals to side BC. In square ABCD, side AB equals to side BC equals to side CD equals to side DA. So, side AB equals to side BC. I write it down. Side AB equals to side BC. In square ABCD, side AB equals to side BC. AB equals to AS plus SB. Again, AB equals to AS plus SB. And it is equals to side BC. BC equals to BQ plus QC. So in total, according to equation 1, we found out that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. Plus SB, SB equals to x, and it is equals to BQ, BQ also equals to x, plus QC, QC equals to 3 units in its length, according to what is given as the question. So in total, according to equation 1, we found out that AS plus x equals to x plus 3. Here we subtract x from this equation, equation 1, so x will get cancelled. And we left only if AS is equal to 3 units in its length. Right, so the missing 97 AS is equal to 3 units in its length. So I'll write it down. AS, this is 97 AS, that is equal to 3 units in its length. In the next step, we will do a construction. That is to say, from this point P, we will draw perpendicular on the radius SO. Again, from point P, we will draw perpendicular on the radius SO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SO. This point is point N. By doing this construction, We created here the small quadrilateral AP and S. Inside the small quadrilateral AP and S, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this 4th missing angle. In total, they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4th missing angle must be equal to 90 degrees in its size. So, inside the small quadrilateral A, P, and S, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So, we relate to the small quadrilateral A, P, and S as a rectangle because it has 4 right angles. So, quadrilateral A, P, and S is a rectangle, according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle AP and S, side AP equals to the opposite side NS. But AP equals to 1, therefore NS must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the same rectangle AP and S, side AS must be equal to the opposite side NP. But AS equals to 3, therefore PN must be also equal to 3 units in its length. What is the length of the missing line segment NO? From the drawing, it is very easy to see that NO equals to SO minus SN. So write it now. NO equals to SO, that is the radius of the circle, minus SN. So in total, NO equals to SO, that is the radius of the circle, that is equal to X, minus SN, that is 1. So in total, NO equals to X minus 1 units in its length. So that is known, NO equals to X minus 1 units in its length. In the next step, we'll join points O and P together by straight line. OP is of course the radius of this circle, that is equals to X. So in the next step, I'll copy the right green triangle P and O in a new page, and we'll implement the Pythagoras theorem on this right green triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right green triangle P and O that I covered from the original drawing. According to the Pythagoras theorem, in this right triangle P and O, PO square, that is the square of the hypotenuse, equals to PN square plus NO square. So I write it down. PO square, that is the square of the hypotenuse, is equal to PN square plus NO square. The length of the hypotenuse PO is x, therefore PO square is x square, and it is equal to Pn square. Pn is 3, therefore Pn square is 3 square, that is 9, plus NO square. NO is x minus 1, therefore NO square is x minus 1 squared. So in total, according to the Pythagoras theorem, we should find out that x squared equals to 9 plus x minus 1 squared. Here we'll open the brackets of this expression and we get that x squared equals to 9 plus x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x. So here we have x squared on both sides of the equation, so x squared will get cancelled. So in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 2x. So in total we should find out that 0 equals to 10 minus 2x. Here we add 2x to this equation and we get that 2x equals to 10. So here we divide this equation by 2 and finally we get that x equals to 10 over 2, that is 5. So actually found out that the length of the hypotenuse PO is 5, but x is also the radius of this circle. We actually found out that the radius of this circle, x equals to 5 units in its length. Our mission is to find out the area of this circle. So actually the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So the area of our circle equals to pi x squared, and the radius x equals to 5. So the area of our circle must be equal to pi times the radius x, that is 5 squared. So it is pi times 5 squared. So it is pi, and 5 squared is 25. So in total we have found out that the area that we are looking for in this question, that is the area of this circle, equals to either 25 pi square units, or in terms of numbers, the area of this circle is equal to 78.54 square units. And that is the answer to the question. I repeat again, I actually found out that the area of this circle is equal to either 25 pi square units, or in terms of numbers, the area of this circle equals to 78.54 square units. So we finish with the first method. In the next step, I'll present to you how to find out the area of this circle according to the second method. Actually, this is square ABCD. We know that AP equals to 1 unit in its length, and CQ equals to 3 units in its length. And our mission is to find out the area of the circle. So first of all, we know that all the angles inside the square are right angles. So those four angles are all right angles. So this is a right angle. This is a right angle. This is also a right angle. And finally, this is a right angle. In the next step, we define the center of this circle. This point is point O, and we define the point of tendency of tangent AB with this circle. This point is point S. In the next step, we focus at this point, point B. In relation to the circle, point B is defined as a common external point because it is not located inside the circle but outside the circle, so it is a common external point. For the common external point, point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. So I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle. This is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, the length of tangent PA is equal to the length of tangent PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common external point, point B, from this common external point, point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BS equals to BQ. So I'm writing down. According to rule 2, the length of tangent BS is equal to the length of tangent BQ. So if we define the length of this tangent BS as x, then the length of this tangent BQ must be also equal to x because they are equal to each other according to rule 2. We also know that all the sides of square ABCD are equal to each other. That is to say, side AB equals to side BC equals to side DC equals to side DA. So side AB equals to side BC. So I write it down. Side AB equals to side BC in square ABCD. AB equals to BC. AB equals to AS plus SB. AB equals to AS plus SB, and it is equals to BC. BC equals to BQ plus QC. So in total, according to equation 1, we found out that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. Plus SB, SB is x, and it is equals to BC. BC equals to BQ, that is x, plus QC, that is 3. So in total, according to equation 1, we actually found out that AS plus x equals to x plus 3. Here we subtract x from the equation 1. So x will get cancelled, and we left only with AS that is equal to 3 units in its length. So actually, this is line segment AS that is equal to 2 units in its length. In the next step, we will extend line segment AD by straight line until it touches the circle. And we will define the touching point of the extended line segment AD with this circle. This point is point M. In the next step, we will focus on the common external point A. Again, point A is external point in relation to the circle. So from the common external point A, we have here tangent AS, and from the same common external point A, if we draw a straight line here, we get that we have also chord PM. And for that reason, we can implement rule 10 on the common external point A. So I'll repeat quickly on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is a coordinate circle and PT is a tangent to the circle at point T, so in this, again, PT is a tangent to the circle at point T, then in this domain the following equation is true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can definitely implement rule 10 in our drawing. Why? In our drawing, if we focus on the common external point A, we have tangent AS that is tangent to the circle at point S, and from the same common external point A, we have here chord PM. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10 in our drawing. According to rule 10, AS square equals to AP times AM. Again, AS square equals to AP times AM. So I write it down. According to rule 10, if you focus on the common external point A, the following equation will be true. AS square equals to AP times AM. So if it again, if we focus on the common external point A, according to rule 10, AS square equals to AP times AM. AS equals to 3, therefore AS square is 3 squared, that is 9, and it is equal to AP times AM. AP is 1, and AM, in total AM equals to AP plus PM. So according to rule 10, in total we found out that 9 equals to 1 times AP plus PM. So 9 equals to 1 times any number is the same number, so we can ignore 1 here, and when we multiply anything by 1, it will not change the value of the expression. So 9 equals to AP plus PM. AP is 1, so we substitute AP by 1, and we get that 9 equals to 1 plus PM. So here we subtract 1 from this equation, and finally we get that PM equals to 9 minus 1 is 8. So if we found out that chord PM equals to 8 units in its length. In the next step, we'll do a construction, that is to say, from point O, that is the center of the circle, we'll draw perpendicular on chord PM. Again, from point O, we'll draw perpendicular on chord PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PM. This point is point N. So we actually drew perpendicular from the center of the circle, that is to say from point O on chord PM. And for that reason, we can implement here rule 11. So I'll repeat quickly on rule 11. According to rule 11, the perpendicular to a chord drawn from the center of the circle bisects the chord. So in the drawing we have a circle. This is point O, that is the center of the circle. So from point O, that is the center of the circle, we do perpendicular OM on chord AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 11, whenever you draw a perpendicular from the center of the circle towards any chord, in this case it's chord AB, the perpendicular OM bisects chord AB. If OM bisects chord AB, it means that AM equals to MB. AM equals to MB. And also, this equals to AB over 2. So AM equals to MB equals to AB over 2 because of the fact that chord AB is being bisected into two halves. Each half equals to AB over 2, of course. So the first half is AM, the second half is MB, and each half equals to AB over 2. So AM equals to MB equals to AB over 2. So whenever you draw a perpendicular from the center of the circle towards any chord, the perpendicular will bisect the chord. In this case, perpendicular OM bisects chord AB. This is to say AM equals to MB equals to AB over 2. So we can definitely implement rule 11 in our drawing. Why? Because in our drawing, we have from the center of this circle, that is to say from point O, we draw perpendicular ON on chord PM. So actually all the requirements of rule 11 are satisfied, and therefore we can implement rule 11. According to rule 11, the perpendicular ON bisects chord PM. If ON bisects chord PM, it means that ON divides chord PM into two halves. Each half equals to PM over 2. That is to say, the first half is PN, and it of course equals to the second half, that is NM, and each half equals to PM over 2. So I write it down. According to rule 11, this drawing, PN ON bisect chord PM. So the first half is Pn, and it of course equals to the second half, that is Nm, and each half equals to Pm over 2. So repeat again. According to rule 11, perpendicular ON that is drawn from the center of the circle, that is to say from point O, bisects chord PM. That is to say it divides chord PM into two halves. Each half equals to PM over 2. So Pn equals to Nm equals to PM over 2. Pn equals to Mn equals to PM over 2. Pm is 8, therefore Pm over 2 is 8 over 2, that is 4. So in total, from this equation, eight over 2 is 4. Again, Pm over 2 is 8 over 2, that is 4. So from this equation, from this another equation, we derive that Pn equals to 4 units in its length. Again, Pn equals to 4 units in its length. So actually, this is line segment Pn that is equal to 4 units in its length. So I write it down. Pn equals to 4. Therefore, in total, An equals to AP plus Pn. That is to say, it equals to AP that is 1 plus Pn that is 4. So in total, An equals to 1 plus 4 that is 5. In the next step, we'll join points O and S together by a straight line. OS is of course the radius of the circle because it starts from point O, that is the center of the circle, and ends at point S, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OS is the radius of the circle. Here we have the radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So actually, by doing this construction, we can deduce quadrilateral ANOS. Inside this quadrilateral ANOS, we have 1, 2, 3 rectangles. The sum of three rectangles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside this one quadrilateral ANOS we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to quadrilateral ANOS as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ANOS, side AN must be equal to the opposite side OS. But AN in total equals to 1 plus 4, that is 5. Therefore, OS must be also equal to 5 units in its length. OS is the radius of the circle. So the radius of the circle equals to 5 units in its length. Okay, the radius of the circle equals to 5 units. Our mission is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is 5 and the radius squared is 5 squared. So the radius of our circle equals to pi times 5 squared. 5 squared is 25. So in total this expression equals to 25 pi. In terms of numbers, it is equal to 78.54 square units. So actually, in both methods, we found out that the area of this circle is equal to either 25 pi square units, so in terms of numbers, it is equal to 78.54 square units. So in the next step, I will summarize the lecture. We start with the first method. So in this lecture, we found out the area of this circle using two different methods. So in the drawing, we have a circle and we also have square ABCD. We know that AP, this is line segment AP, that is equal to 1 unit in its length. This is line segment QC, that is equal to 3 units in its length. Again, our mission is to find out the area of this circle. So first of all, we know that ABCD is a square, therefore all those 4 angles are right angles. We define the center of this circle, this point is point O. We define the point of tendency of tangent AB with this circle, this point is point S. In the next step, we join points O and S together by slide 9. OS is the radius of the circle. We define the radius of the circle as X. So here we can actually implement rule 1. Why? Because we have the radius OS that is equal to X. The radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by slide 9. OQ is of course the radius of the circle. This is equals to X according to our definition. Again, we can implement here rule 1 because we have the radius of Q that is drawn to point Q. That is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. So actually, inside quadrigonal SOQB, inside this quadrigonal SOQB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle. In total, they must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrigonal is equal to 360 degrees. And therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrigonal SOQB, we have 4 right angles. And according to rule 5, any quadrigonal that has 4 right angles must be this left angle in front of the square. So we relate to quadrigonal SOQB, it's a left angle because it has 4 right angles. But we also know that the opposite sides of a left angle are equal to each other. So in left angle SOQB, side SO must be equal to the opposite side QB. But SO is X, therefore QB must be also equal to X. Likewise, according to the same rule, in the same left angle SOQB, side QO must be equal to the opposite side SB. But QO is X, therefore SB must be also equal to X units in its length. So, in total, we should find out that quadrigonal SOQB is not a rectangle but a square because of the fact that all 3 sides are equal to each other. Each side of this square equals to X. Okay. We also know all the sides of a square are equal to each other. So in square ABCD, side AB equals to side BC equals to side CD equals to side DA. And especially side AB equals to side BC. Repeat again. is square ABCD, side AB equals to side BC. AB equals to AS plus SB. AB equals to AS plus SB, and BC equals to BQ plus QC. BC equals to BQ plus QC. So in total, we found out that according to equation 1, AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is, plus SB. SB is X, and it is equals to BC. BC is BQ, that is X, plus QC, that is 3. Again, BC is BQ plus QC, and BQ is X, and QC is 3. So in total, AS plus X equals to X plus 3. So here we subtract the X on this equation, equation 1, and we found out that AS equals to 3 units in its length. This is 97 AS, the missing 97 AS equals to 3 units in its length. In the next step, we did a construction, that is to say, from this point P, we draw perpendicular on the radius SO. Again, from point P, we draw perpendicular on the radius SO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SO. This point is point N. By doing this construction, we created the small quadrilateral AP and S. Inside the small quadrilateral AP and S, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral AP and S we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a right angle if not a square. So next to the small quadrilateral AP and S as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle AP and S, side AP must be equal to the opposite side NS. But AP is 1, therefore NS must be also equal to 1 unit in its length. Likewise, according to the same rule, in the same rectangle AP and S, side AS must be equal to the opposite side PN. But AS is 3, therefore PN must be also equal to 3 units in its length. What is the length of this missing 97 NO? From the drawing, it is very easy to see that NO equals to SO minus SN. Again, NO equals to SO minus SN. So NO equals to SO, that is the radius of the circle, that is X, minus NS, that is 1. So in total, NO equals to S minus 1 units in its length. In the next step, we join points P and O together by straight line. PO is of course the radius of the circle, that is equal to X. In the next step, I copy the right green triangle P and O in a new page and we implemented the Pythagoras theorem in this right green triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right green triangle P and O that I copied from the original drawing. In this right triangle P and O, PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. Again, PO squared equals to PN squared plus NO squared. The hypotenuse PO is X, therefore PO squared is X squared, and it is equals to PN squared. PN is 3, therefore PN squared is 3 squared, that is 9, plus NO squared. NO is X minus 1, therefore NO squared is X minus 1 squared. So in total, according to the Pythagoras theorem, I shall find out in this right triangle P and O, X squared equals to 9 plus X minus 1 squared. Here we open the brackets of this expression and finally found out that X squared equals to 9 plus X minus 1 squared. X minus 1 squared equals to X squared plus 1 squared, that is 1, minus 2 times X times 1, that is minus 2X. So here we have X squared on both sides of the equation, so X squared will get cancelled. In this side of the equation, after we cancel X squared, we left with nothing, that is to say 0. On the other side of the equation, we have 9 plus 1, that is 10, minus 2x. So in total, we found out that 0 equals to 10 minus 2x. Here we added 2x to this equation, and finally found out that 2x equals to 10. Here we divided this equation by 2 and find out the radius of the circle and then also the length of the approach PO. X equals to 5 units in its length. Okay, again, the radius of this circle, x equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. But x is 5, therefore x squared is 5 squared. So in total, the area of our circle must be equal to pi times 5 squared. 5 squared is 25, so in total this expression equals to 25 pi. Again, the value of this expression, in total is 25 pi. So if we found out that the area of this circle equals to either 25 pi square units, or in terms of numbers, the area of this circle equals to 78.54 square units. We finish with the first method. In the next step, I present to you how to find out the area of this circle according to the second method. So first of all, because of the fact that ABCD is a square, all those 4 angles are at angles. And in the next step, we actually focus on this common standpoint point V. From this common standpoint point V, we have 2 tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BS equals to BQ. Again, according to rule 2, BS equals to BQ. So if we define the length of BS as x, then the length of BQ must be also equal to x because they are equal to each other according to rule 2. And we also know that all the sides of square ABCD are equal to each other. That is to say, side AB equals to side BC equals to side CD equals to side DA. And especially side AB equals to side BC. So in square ABCD, side AB equals to side BC. AB equals to AS plus B to AS plus SB. AB equals to AS plus SB, and BC equals to BQ plus QC. BC equals to BQ plus QC. So in total, according to equation 1, we have found out that AS plus SB equals to BQ plus QC. So it is AS plus SB. SB is x, and it is equal to BQ plus QC. BQ is x, and QC is 3. So in total, we have found out that AS plus x equals to x plus 3. So here we subtracted x from this equation and finally found out that the missing line segment AS equals to 3 units in its length. This is the missing line segment AS that is equal to 3 units in its length, exactly according to the first method. Okay. In the next step, we extended line segment AD by a straight line until it touches the circle. We define the touching point of the extended line segment AD with this circle. This point is point M. So if we focus on the common standpoint point A, from the common standpoint point A, we have tangent AS that is tangent to this circle point S, and from the same common standpoint point A, we have also here chord PM. So actually, all the requirements of rule 10 are satisfied, and therefore according to rule 10, we get that AS square equals to AP times AM. Again, according to rule 10, AS square equals to AP times AM. Okay, again, according to rule 10, if you focus on the common standpoint point A, the following equation will be true, that AS square equals to AP times AM. AS is 3, therefore AS square is 3 squared, it is 9. And it is equals to AP. AP is 1 times AM. AM in total equals to AP plus PM. Again, AM in total equals to AP plus PM. Again, AP is 1 and AM is AP plus PM. A squared is 3 squared, it is 9. So in total, 9 equals to 1 times AP plus PM. Again, AP is 1. So solve AP by 1 plus p.m. So in total, we found out that 9 equals to 1 plus p.m. Here we subtracted 1 from this equation and finally found out that the missing code p.m. equals to 9 minus 1, that is 10. This is called p.m. It is equals to 8 units in its length. In the next step, we did the construction. That is to say, from this point O, that is the center of the circle, we do perpendicular on chord PM. Again, from point O, that is the center of the circle, we do perpendicular on chord PM. So clearly, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PM. This point is point N. So, because of the fact that we have here perpendicular from the center of the circle, that is to say, from point O, on chord PM, we can implement here rule 11. According to rule 11, the perpendicular ON that is run from the center of the circle, that is to say, from point O, bisect chord PM. Perpendicular ON bisect chord PM. If perpendicular ON bisect chord PM, it means that it divides chord PM into two halves. Each half must be equal to PM over 2. So the first half is PN, and the second half is NN, and each half equals to PM over 2. So according to rule 11, perpendicular ON bisect chord PN. Each half equals to PM over 2. So the first half is PN, the second, and it is of course equals to the second half, that is MN, and each half is PM over 2. But PM is 8, therefore PM over 2 is 8 over 2, that is 4. From this long equation, we derive that Pn equals to 4 units in its length. Okay, Pn equals to 4 units in its length. This is line segment Pn is equals to 4 units in its length. In the next step, we join points O and S together by a third line. We join points O and S together by a third line. OS is of course the radius of the circle, and we have the radius OS. The radius of the circle OS is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral ANOS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth facing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth facing angle must be equal to 90 degrees in its size. So inside quadrilateral ANOS, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be tesseract and quadrat square. So we relate to quadrilateral ANOS because it's a rectangle because it has 4 right angles. So quadrilateral ANOS is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ANOS, side AN must be equal to the opposite side OS. But AN in total equals to 4 plus 1, that is 5. Therefore, OS must be also equal to 5 units in its length. OS is the radius of the circle, so the radius of the circle equals to 5 units in its length. Our mission is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is 5, therefore the radius squared is 5 squared. So in total, the area of our circle must be equal to pi times 5 squared. 5 squared is 25, so in total its expression equals to 25 pi. So in total, we should find out the area of this circle in both methods is equal to either 25 pi square units, or in terms of numbers, the area of this circle equals to 78.54 square units. Okay, thank you very much.